So we have two different situations that we talked about for multiplicity, okay? Binomial case was the first one. Here we have m factorial is divided by capital N factorial, m minus n, okay? Because if something isn't an n-type outcome, then it's obviously whatever the other outcome is out of the two. So this is where m is the possible, so let me change this. I don't like how I just written in here. Okay, multiplicity is the possible number of ways, okay? This is, I don't know, multiplicity. Multiplicity is the possible number of ways to arrange m total things, whatever it is, from a collection of n objects, things, whatever it is. Okay. N's all the ways you're going to, you have this is your total number, and then you have a collection of n different types. For binomial case, there are only two categories of n. So this is heads, tails, on, off, bound or unbound for, say, a ligand binding to a receptor, or double-stranded, not double-stranded for DNA, something like that. Folded or unfolded for the protein. Okay. And we said binomial case is actually very biologically relevant for us. And then we also had our general case, where multiplicity is given by m factorial. Okay, so still our total number of ways we can arrange the things. It's the total number of all the things we have. And then they fall into more than two categories. Okay? So we're multiplying across all the number of things that are in category type 1, category type 2, through to n sub t. Okay? So for our general case, we have multiple categories, t, each with some number of objects n. And just to remind everybody, a factorial for some number, just now lowercase n is what we're using, it would be n times n minus 1 times n minus 2 down to 2 times 1. 0 factorial is equal to 1. So just a note, obviously the binomial case is just the general case when you only have two categories, and it simplifies to just n1 and n2. So I actually don't remember what's on the equation sheet. When we get through today, I will remove off the bottom whatever we didn't get to and isn't relevant for. Oh, I give you both. Both of them are there. So here are our equations for calculating multiplicity again. And you will receive these two equations on the equation sheet. This was our example case for last time when we were placing 6 different bases that we had into a 6-string in order. Okay. How come we said that we knew this was going to have higher multiplicity even before doing the math, the left side? Yes?
The left side had another line.
Yeah, it had an extra letter. It had more categories. It looks more random. It has more stuff. Okay. In this case, all of the bases were indistinguishable. What does that mean? What did indistinguishable mean? Or alternatively, what does distinguishable mean? Yes?
Distinguishable means that all of it's the same.
Great, right, so what she was saying is that like an A from an A, I couldn't tell it apart, it's indistinguishable, but an A from a G or an A from a T, I can tell it apart, it is distinguishable. Now, could I write a problem where I tell you, oh, I've dyed all my A bases with some fluorescent signal and I can no longer tell them, I can tell them apart. I made A1 blue and the next one's red. Can the A's now be distinguishable? Sure, and so this is where you need to just pay attention to what has been set up for you in the problem and make sure you're doing it right. Generally speaking, if things are distinguishable, multiplicity goes up. And so this was our simplified example of that, if you could tell the A's apart versus if you couldn't, and what that did to multiplicity. So this is an example from your book. They're talking about having some type of virus that is able to bind to up to 6 RNA molecules. And each of those RNA molecules can be tagged with a fluorescent dye, and then this is a microscopy, a micrograph that was collected in that way. And so you can see all these dots represent one of these virus spots with a fluorescent on it. And essentially, what they were showing here is that as you either, with time, as photo bleaching happens, so the fluorescence is going away, you can see a drop off in intensity of this fluorescent signal, how bright it is. From some initial point, as you wait, there'll be a drop off, then maybe another drop off until you're no longer seeing a signal, and that let them count how many receptors actually bound to the virus, up to 6. Okay. So this is the experiment that sort of came from. Okay, and receptor ligand binding is a really practical biological application where multiplicity and this binomial situation is very relevant. So here we have a monomeric receptor, okay? We can call empty, you could call it tails if you want. I'm cool with just empty, unbound, bound, whatever, however you want to code them, okay? So you have 2 options for a monomeric receptor. It either is empty or it is bound by some ligand. Multiplicity in both of these cases is 1. Right? There's only one way for it to be attached, there's only one way for it not. If you have a dimeric receptor, so now if you have one receptor and it has 2 different binding sites, okay, to accept ligand. So you could have, there's only one way for both sites to be empty, one way for both sites to be bound, but there are 2 ways for one site to be bound, here or here. So in the body, which of these situations is the one that's most likely to be found? One ligand bound, okay? Having half of all the receptors filled is the most likely scenario, okay? Because multiplicity is the highest, it can happen the most ways. And that would facilitate maximizing entropy. So let's say I have 500 dimeric receptors, and I want to calculate multiplicity. What is my capital M? I have 1 vote for 500. Anyone else agree or disagree? I have 1,000. Who says 500? Who says 1,000? Who says it's something else? Who couldn't care less? It's 1,000. I have 2 binding sites. Okay. I have 500 ligands that are bound or could be bound. What is N? Each receptor has 2 sites. I have 500 dimeric receptors. Each one of them has 2 possible sites that a ligand could attach to, giving me 1,000 sites they could possibly attach to. Then I have 500 ligands that could attach in those 1,000 sites. So to get multiplicity, I'm interested in 1,000 factorial over 500 factorial, 500 of them being bound, and 500 of them being unbound. So we're going to calculate the multiplicity of that. Can we do the factorials for that? Can your computer do it? No. MATLAB will give you an error back if you try to put in 500 factorial. It maxes out at like 150. It'll just say no. We have to approximate it with something else, okay? So let's go back to here. So for our example case, we had 500 dimeric receptors having 1,000 total binding sites. This was capital M, total spots we can fill. And we're asking, how can we fill these sites? So there's sort of two ways, right? It's binomial case, we're either bound by ligand or we're not. This is representative of binomial case. If 500 are bound, what is the multiplicity? How many different ways can that happen? The multiplicity will be given by 1,000 factorial divided by 500 factorial times. This is just 1,000 minus 500 if you want to look at the binomial case. So we have an approximation for doing large factorials, okay? Since even our computers are going to error once they exceed about 150. And it's called Stirling approximation.